Okay, the problem we're going to be looking at here is going to be 647. And the actual illustration is up here at the top of the column on page 129, but the problem statement is on the previous column right here towards the bottom. Okay. So it says that each handle of the bolt cutter shown acts like a simple lever for dimensions and input forces that are given. Find the force exerted by pin B on handle ABD. So it's going to be the, if we look up here, what are the reactions at that pin support? It's considered a support in this application. And then what is the force exerted by the handle on bolt A? Okay, on bolt A. Now they're giving us the dimensions here, A, B, and D, and those are going to translate up here to the dimensions that we see. Okay, so free body diagram first. Now this is going to be very similar to the last practice problem that we did in this particular module. So if you wanted to look back at that for the formatting, it's going to be just like that problem. Okay, so I am going to start by saying that this is problem, let's see, 647. Right. And I'm going to put my convention in the upper right-hand corner right away so I don't forget. And then I'm simply going to draw my free body diagram. Now my free body diagram is going to be simplified. Okay, so right about here, I'm going to identify point B. Okay, out here, it's going to be point A. Okay, and out here is going to be point D. Now I know this handle isn't straight, but by the principle of transmissibility, okay, these are pretty much in line. We can move this point D along its line of action up to what would be a horizontal line going all the way through. So that's how I am modeling this, okay? Now the dimension between A and B is 1.875 inches. The dimension between B and D is 28 inches. And the force that, oops, my camera disconnected. Hold on, I don't know why. We'll just go back into it. Should reconnect. Sorry about that. Oh, come on. There we go. Okay. And the force at D here, PI, is 40 pounds. Now, because we're on the bottom, PI is acting up. Do you see that? PI is acting up. So we're going to show our vector going up, and we know this to be 40 pounds. Okay. Now, that's the one applied load that we know, but there is a support at the pin, and there's going to be a force that we are going to exert on the bolt by this bolt cutter. So we have to put those two in there. Now, for right now, I'm going to assume that if I am, and again, remember, if we don't assume the right direction, our math will tell us otherwise. We'll get a negative value as a final answer. But if I'm clamping these two together, and this is the pivot point, simple lever, that would mean that at A, we're going to be pushing down on that bolt, right? So I'm going to assume the direction going down at A. It should be pretty significant. So we're going to call this, we're just going to call it A, force A. You can call it AY. How about that? It's in the Y direction. Now at B, this is a pin. So thinking back into module 5, a pin reaction always has two components. It's going to have an X and a Y. So I'm going to show an X and a Y reaction here. BY and BX. I don't know which way they're going. Quite honestly, I'm not exactly sure. Okay. But I know that there is a force going in each one of those directions. So I need to put my vectors there with arrowheads, assume a direction, and our math will tell us if we did okay or not. But we want to just make sure that we have everything accounted for. Okay. So that is our free body diagram for one of the handles of this bolt cutter. Okay. So our second step then, I always want to look, if there was any forces that would be at angles, our second logical step will always be components, right? as we've seen. But everything here is vertical or horizontal, so we don't need to put anything in components. So the next step is going to be our equations of equilibrium. Okay. And we have three of them. We have some of the forces in the x equals 0. And I'm going to put some of the forces in the y equals 0. And then we have some of the moments around a point equal to 0. And we can start wherever with any one of these. All right. And I'm going to kind of put down here some of the moments, but we're going to have to put a little letter there is equal to 0. So those are our three equations of equilibrium to help us to solve for AY, BY, and BX. So, Drew, what are you thinking? Which one should we do first? You want to do some of the forces in the Y? Okay, let's do it. Let's write what we have here based on the directions that we assumed. Now, you may have assumed a different directions. That's okay. But this is what I assumed. So I have AY going down. That means I'm going to have a negative AY. I have BY going down, negative BY. And I've got a positive 40 pounds. Okay. And I have to set that equal to 0. On the left-hand side, this was summing my forces in the Y, equal to 0. I have been taking points off people's homework that has been coming in that doesn't have the equal to 0. I look for that. Remember, it's an equation of equilibrium. So it has an equal sign and it has two sides. All right. Don't, like on the next line, combine things and then all of a sudden magically solve for something. That's not how we work here. Okay. So as we can see here, I've got two unknowns. So I'm just going to leave this as negative AY minus BY is equal to negative 40 pounds. I'm going to just put the 40 on the other side. Because all of these values are negative, I can make them all positive, can't I? Right? So I'm going to do that. So AY plus BY is equal to 40. So that's as far as I can go with that one. That's okay. Leave a little bit of space down below and we'll come back and we'll fill it in as we can. So what do we want to do next as we look? We've got two other equations of equilibrium. Yeah, let's do the forces in the x. So we've got some of the forces in the x equals 0. I've got only one force in the x. I assumed it was pointing to the right, so that would be bx is equal to 0. That is its magnitude, okay? All that means is there's not a side load, identified here. And that's okay, but it does restrict in the x direction. All right, and then we have one more equation of equilibrium. Now, since we have two unknowns here at A and at B, where you want to sum your moment around, we have to identify that point, is going to be one of those 2 points, because then it takes that out of the equation. So Drew, which point would you like to sum around, A or B? A, okay, so I'm going to fill in my little cloud here. That's going to be sum the forces around A. That means I'm going to put my finger on A, and then I'm going to start pulling in the direction of offset forces. So I've got an offset force BY unknown that's going to cause rotation. So it's going to be BY times its perpendicular distance. So BY here times 1.875 inches. Okay. And when I look at the rotation that's created, it is going to go clockwise. And according to my convention, that is negative, right? Then I'm going to go back up here. The other force that, BX, let's see what BX would do. BX is just going to pull there because if I push it back along its line of action, it goes right through the point. There is no offset distance. It's not going to cause rotation, so we don't even put it in. But the 40 pounds will. So 40 pounds is going to rotate in a counterclockwise direction. So I'm going to say 40 pounds times, it's going to be 1.875 plus 28 is its perpendicular distance all the way to there. So that's going to be 29.875 inches. And the direction of rotation is counterclockwise, so that's positive according to our convention. Those are the only forces causing rotation. So now we can set our moments equal to 0. Again, I always look for this. Even if your answers look good, I don't just look at the final answer. I look at how you set it up. And this is something that you have to have there. Okay, so now as I look, I just have one unknown. Okay, so what you'll do here is you'll solve for by. Okay, now what I'm going to do here, Drew, is you're going to solve for by, right? So you're going to get whatever by is equal to. Boom, 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 boom. You're going to get that number. All right, and that's going to be in pounds. So you'll do that work. Once you get by, you can then plug it in up here to solve for ay. Okay, so is that enough for you to finish it up? Okay. All right, well then we will stop the recording here.